So last time we wrote out the work energy theorem, we said that when work is done, the system energy changes. Now, by system energy, we mean the sum of the kinetic and potential energy, and another way to refer to that is the mechanical energy of the system. So if you do, say, apply a force in the direction of motion, that will increase the energy of the system. And if there is dissipation, say like a force of friction, then the work done will be negative. The force will be opposite to motion, negative work, and then the mechanical energy of the system will decrease. But there's another way of looking at that. And that is to say that although the energy of the system can go up or down, the energy of the universe doesn't ever change. And so what this term here represents is different forms of energy. So if there's an applied force, that would be, say, like chemical energy in your muscles, a portion of the chemical energy in your muscles that was being converted into motion energy. In friction, in the case of friction, this of course is thermal energy. So to illustrate that, we'll do a really, really simple example. Let's imagine that you just take a ball and it starts off at rest in your hand. So there's no speed, so the kinetic energy is 0. And if we call this the 0 of height, then there's no height energy or potential energy at that point either. So you do some work. As a result of the work, it's moving. Now, it's also gone up a little bit, so you'll see 1 joule of potential energy here. If you've done 30 joules of work, right, that's your work term here, then you must have 29 joules of kinetic energy. Now, we'll come back to what this is, interpreting this in a few minutes, but this was 0, this was 30, so this has to be 30, right? 29 plus 1. Okay, now as this thing rises and falls, it turns out that the kinetic and potential energy, the total of those two remain the same, so that when you've got 15 joules of height energy, you've got 15 joules of kinetic, right? So the total here is the same. Now this is just true for the middle free fall part of the motion. Up here at the top, it's going to stop, so there'll be no kinetic, so that means it's all got to be in potential form, 30 joules of potential. And then down here at the bottom, we're back down at the 0 of height, so there's no height energy, so there must be 30 joules of kinetic motion energy. That says 30. So the total was 0, but then we did 30 joules of work and we increased the energy of the system. After that, there was no work done. The only force doing work is gravity, and gravity work is taken care of by potential energy. So there's no other forces doing work, so the total of the kinetic and potential stays the same. Now, when you catch this object and bring it to rest, then that catch is doing negative work. You end up at rest and at the 0 of height, so you must have done minus 30 joules of work in catching it. So let's look at this problem then in the context of the work energy theorem. So here's the diagram again, and here's a nice little chart for you, a nice convenient chart. And now, so we want to say what's happening with the mechanical energy of the system. Well, when you threw it, there was 0 initial mechanical energy, and then we ended up with 29 plus 1, or 30 joules of mechanical energy. And that was as a result of the work that we did. Now, in the universe perspective, that work is just chemical energy. And so what we're really seeing is a transformation from chemical energy into kinetic and potential. And the total remains constant, because the energy of the universe is constant. The energy of the system can change. Now, when the ball was rising and falling, there was no change. And the sum of the kinetic and potential, or the mechanical energy, was constant. And that term was 0. Now, when you caught it, again, we had 30 joules of initial mechanical energy. Work was done and we ended up with nothing. Now, that work term just represents heat energy loss. And so what happened there is that kinetic energy was converted to heat energy. And so the energy of the universe was constant. So what we see here is that this term, this work term, in some cases is positive if you're increasing the energy of the system. In some cases it's negative in the case of dissipation. And in some cases it's zero. And so that term there has a couple of interpretations. We can say it's the change in system energy. It's positive if you're pushing in the direction of motion. It's negative if you're pushing opposite. And it can be zero if you have a conservative force. So the NC stands for non-conservative forces. And that's things like applied forces and friction that change the energy, that don't conserve the energy of the system. But gravity is a conservative, and if gravity is the only force, then you have a conservative system, and this is zero. So this is the change of system energy. It can be positive, it can be negative, or for a conservative system, it's zero. Another way to look at it, of course, in the energy of the universe approach is it's just other forms of energy. It's, say, chemical energy in the case of an applied force, or it's heat energy in the case of friction. So our understanding then is that we have some system with a certain amount of mechanical energy, and then so we'll apply the work energy theorem, and the key question we'll ask is, are there non-conservative forces? Does the energy of the system change, or is the mechanical energy, which is the sum of the kinetic and potential, is that a constant? So the first example we'll look at here is a pendulum. And it's a pendulum with no air friction. Now, because it has no air friction, this non-conservative work term is zero. There isn't any. And that means that the sum of kinetic and potential energy should be constant. So this is sort of a conceptual example. We see that it's at rest, so there's no kinetic energy here. So that means the total of these should be a constant, and it's 10 here, so the total will always be 10, because there's no gains or losses of energy. There's no other forms of energy. There's just kinetic and potential. So later, if there's 8 joules of height energy, there must be 2 joules of motion. Down here, 0 joules of height, there must be 10 joules of motion energy. And up here, we're still not quite back to where we started. There's 9 joules of height energy. There must be 1 joule of motion energy. So that is a conservative system. There are no gains or losses of energy. If there is friction, then the work done by friction will be negative, and then the sum of the kinetic and potential energies will decrease over time. So the initial mechanical energy, kinetic, and potential will be greater than the final mechanical energy. So here again, we're at rest. We have 0 joules of motion energy and 10 joules of height energy. Down here at the bottom, the total is dropped to 6, so that's a loss of 4. If we lose 2 further, the total was 6, lose 2, the total must be 4, so here there must be 2 joules of kinetic energy. We'll do one more. Here we have a ball rolling down a frictionless track. And so there is no gains or losses of energy here. So that means, again, this total must be constant. Since it starts at rest, that's 0. So we see the total will always be 25. Down here at the bottom, where there's no height energy left, we must have 25 joules of motion energy. And what about this position here? Well, we see we're exactly halfway down. So that means we have half the height energy, and therefore half the motion energy. So this is another conservative system, and mechanical energy is a constant. Here's a non-conservative system. Because we are pulling on it, we expect that there will be a gain in the energy of the system. And this mass is starting off here. It's all in motion. It's moving at constant speed, so it's still going at the same speed up here. Here we were at the 0 of height, so the total mechanical energy was 800. Up here, what's happened? Well, because the speed is constant, the kinetic energy must be the same as it was below. So now we have a total of 2,000 joules of mechanical energy. So there has been 1,200 joules of work done on that system. One last conceptual example here. This is just a mass in free fall. And if it is in free fall with no air friction, then the sum of the kinetic and potential energy will be constant. And remember, this means mechanical energy. This means the sum of kinetic and potential. So let's see. Oh, this is a calculation question. Okay, so we are starting from rest, so this is 0. The potential energy is mgh, you'll recall. And so it's 20 kilograms and it's 30 meters high. So that's 20 times 9.8 times 30. So let's see, that should be 58 80 joules. There we go. So the total, and you could check that calculation for me, the total is going to remain the same because there's no air friction and that number is 0. So down here when we're 14 meters off the ground, well, it's the same 20 kilogram mass, so this is 20 times g times 14. Let's see, that's 2856, so that should be 2744, I think. Please check that for me. So 2744 joules of potential energy. That means the kinetic must be 5880 minus the 2744. And then from that you can find the speed that it's going. And we'll pick it up at that point in class. We'll finish this example, and then we'll do sort of a more conventional physics problem involving conservation of mechanical energy, which will lead us into our project.